Section 4.2, Simplifying Expressions. We're going to start off with a definition of like terms. Terms are pieces of an expression that are separated by an addition or a subtraction sign, and like terms are terms that have exactly the same variable factor. So for example, I would say that 5x plus 9x are like terms. First of all, we have terms because the addition separates it into two pieces or two terms. And then they're like terms because they both have the same variable factor. The variable factor in each one is x. The numbers out front are different. That's okay. It's about the variables for them to be like terms. And one of the things that we try to do with like terms is to combine them. And officially, the math on that is we use the distributive law to write like terms as a single term. And I'm going to go ahead and show you what the math on that looks like with that example up here. So let's take that example, copy it down here, and see how the distributive law applies to combining these. So if you have 5x plus 9x and they have this variable factor in common as an x, well, the distributive property as we normally would use it says if you have a factor out front of an addition, then you can multiply in and distribute that a to each of the terms and get ab plus ac. What we're going to do down here is the opposite. To say if they have something in common, we could pull it out front or off to the right, which is what I'm actually going to do in this case. So if I have the x in each one of those, then I can factor that off to the right. I'll just show that first. So I've kind of factored that out. And so what would be left? Well, the 5 would still be here from the first term, the plus sign would still be there, and the 9 would still be there from the second term. And you could check that by multiplication. If you thought of distributing that x back in, you'd be right back at the 5x plus 9x where we started. And the advantage of doing that is now you have the 5 plus 9 in parentheses together, and if we follow order of operations, we'd work inside those parentheses first, and 5 plus 9 would give us 14, and we would still have that x there, or 14x. So we get 5x plus 9x is equal to 14x. And so that's the way the math on that works. I think if you looked at that, you might have thought about the answer faster, maybe even without using the distributive property. And I'll mention that right down here as well. But first let's just define a new definition, which would be coefficient. And the coefficient of a variable term is the constant factor of that term. So the constant factor means the numerical factor. So on 5x that would be a 5, and on the 9x that would be a 9. And as you may have suspected when you looked at this, the quick trick that we could use instead of the distributive property would be that we could simply add the coefficients. So if you tried to apply that here, you'd say if you have 5x plus 9x, you'd have the 5 plus 9, which is 14, and you would still have it as an x, so 14x. And we'll use that quick trick most of the time rather than the distributive property. And it's just worth pointing that out in another kind of setting. Suppose you had 5 chairs plus 9 chairs. Well, what would you have then? 14 chairs. And I think an example like that's important because sometimes when people combine these, they want to add the 5 and the 9 to get 14. But when they have the x and another x, they feel like, oh, should I make it x squared or something like that. But when you're adding or subtracting, you change how many things you have, but you don't change what kind of things you have. So back to the 5 chairs plus 9 chairs. We get 14 chairs, not 14 chairs squared. So it's the same idea here. So let's go ahead and look at some more examples of this. So we're going to go ahead and try and simplify each of the following by combining the like terms. And after we're done with all these, I'll show you a way that you could use the graphing calculator to check your work on these as well. So let's see, 3x plus 6x. If we were to use the quick trick on that, we see these are like terms, they each have the x, and then we would just add their coefficients. So 3 plus 6 would give us a 9x. And then nothing special about that being applied to the letter x. If it's a different variable, we could do that as well. So negative 4p plus 7p, you would just add the coefficients. So I'm going to show kind of the distributive property on this, though you certainly could go ahead and do it in your head. So I'm kind of factoring that p off to the side, or just showing you the addition I'm doing. And what I really wanted to point out there is that the coefficient of this one is not 4, but negative 4. So the addition we're doing is negative 4 plus 7, which would be 3, and then we still have the p there. And there's nothing about this rule that couldn't be applied to fractions. So if you have 9/5 x minus 2/5 x, you still have the same variable piece x on each one of those. And so you still could set that off to the side or factor it out and say what I really need to do is just add those coefficients together, which is 9/5 minus 2/5. Or you could say 9/5 plus negative 2/5 if you really wanted to see it as adding. But writing it as a subtraction or adding the negative would be the same. So we go ahead and carry that out. Luckily here we have a common denominator, and that makes our work a little bit easier. We just need to subtract the numerators. So 9 minus 2 is 7/5, and then we still have the x. And again, you could go just directly to that answer as long as you're comfortable kind of setting that x to the side mentally and saying, all right, what is 9/5 minus 2/5? It's 7/5. And the same thing goes for part B. I could have done that there too, and I normally would. I would have just looked at that and said, okay, -4 plus 7 is 3, and then it's still p. All right, one last example down here. If we have multiple variables, what I usually will do is process through this in an alphabetical fashion, looking for like terms. So I look at the x term and say, do I have a like term with that? Yes, here's another like term over here. So I want to go ahead and combine those together. And the key thing here is what is the coefficient on this term. And sometimes people will say 3, but you have to include that sign out front. So this would be a -3x plus a 6x. If I add the coefficients there, -3 plus 6, opposite sign, so I subtract, bigger one is positive, so I get a positive answer. So -3 plus 6 is 3, and those were x terms to begin with, so there's still x terms after we combine them. And then when you go to look at the other pieces, they don't have like terms. So if I look at the 7y, there's no other y term. When you're asked to combine like terms and there's only one of that type, so it doesn't have a like term with it, you should just copy that over. And then I would do the same thing on the constant term. No like term to that 5, so I would just copy it over. It just said 5, but these are terms, which means as we connect them together, they'll always be connected with either addition or subtraction. And in this case, since that was a +5, I'm going to write +5 at the end. And that would be the answer on that one. Sometimes there's a temptation to combine these, like 3x plus 7y is maybe 10xy or something. But if you have 3 chairs plus 7 tables, you can't say you have 10 table chairs. So when they're a different type of thing, you cannot add them together. All right, let me go ahead and show you how we can check these on the calculator. And we do that by doing 2 different graphs and trying to look to see if they end up having the same look to them. And so what I want to do, let me move this over a little bit more, I'll check part A for you. I want to go into the y equals menu, and for my first function I want to enter what I started out with, which is 3x plus 6x. And then for my second function I want to graph my answer, which in this case was 9x. And what I'm hoping is going to happen is that when I graph these, I'm hoping that line 1 shows up, and then the graph for 2 will come along and hopefully be just right on top of the first one. If that's the case, that would verify they were really the same line. So let me go ahead and show you this. So there goes our first line, and notice the calculator is still working, and so it was still graphing there, but we didn't see anything new. And that was because the second equation was the same as the first one, just in a simplified form. Just for an example on that, let me show you what would happen if we had messed up our work there and made a mistake and actually, say, done an 8x. Then when we graph it, you're going to see the first one come in, and then when the second one comes in, you'll see it this time. It showed up there as a little bit different. So when you see something a second thing get drawn, you're going to know that something went wrong. And one other thing that is a nice way to be able to check that, when you really do just see one thing show up, there is always the possibility that what's happening there is that one of them is in the window and the other one you've made a mistake that made it so different it doesn't even show up in the window. So one way you can check that is to hit trace and just move over here so we can see that point a little better. It actually tells you what equation you're on. So we see that we're on the y1 equals 3x plus 6x equation, and you can see the x and y coordinate. If I press the up arrow or the down arrow, it's going to switch to the other function, y2 equals 9x, And notice the point is still showing there in that same spot, so we can really verify that those two lines are overlapping each other. And if you really wanted to check, you could also see that the x and the y's are the same. And then this is especially handy when you have something with fractions that maybe you were a little bit more nervous about. So let me show you how this would look if we were checking part C. So let me go back into the y equals menu and clear out these two, and enter in what we started out with on this one, which was 9/5, which I'll write as 9 divided by 5 times x, and then minus 2/5, so minus 2 divided by 5 times x. And so that would be where we started, and when we were done simplifying that, we had this 7/5 x, so I'll put that in as my second function. And then again, just like last time, the hope would be that when I graph these, I only see one graph and that it really truly is one on top of the other. So let's go ahead and hit the graph button. So here comes our first one, and then now it's graphing the second one, and I don't see anything new, so that's a good sign. And now I just want to verify that both graphs are really there by hitting the trace button. Again, I'll just move over here to get off that axis a little bit, and you can see up here in the corner that this is y1, which is the two separate terms, but if I press the down arrow, it switches to y2, which is our answer, and yet we're still right on the same spot because those graphs are one on top of the other. Just quick mention in terms of checking these other ones, if you were going to check B, you would just have to still use the X key even though the problem had a P in it. And when you get down to D, if you have one with two variables in it, then this method's not going to work. Let's continue on simplifying our expressions by combining like terms, just looking at a few other situations that can arise. When we look at part E here, the main thing that stands out is the parentheses showing up now. And in the last section, we talked about if there was a negative in front, you could treat that as if it was a -1. And in such a case, you would want to use the distributive property. So if you were to multiply by a -1, that has the effect of leaving the size of the numbers the same but changing their signs. So if I went through and simplified this, the 8x I would just copy, and then I'd start distributing this thinking of it as a -1. So -1 times 3 would be -3, and that's still an x term. And -1 times +7 would be a -7, and that one's still a y term. And I would not distribute that to the next one because it's not inside the parentheses, but I would just copy that one down. And then I start combining like terms once the parentheses are gone. And you do usually want to be careful not to try and combine them until after you've cleared parentheses. So we have x terms that are like terms, so I'll add their coefficients together. 8 minus 3 is 5, and those are still x terms. And then we have our y terms right here that are like terms. Be careful and make sure you attach the negative as part of the coefficient. So we have a -7 plus a -2. They're both the same sign, so we add those up and keep the common sign. So adding them up we get 9, and the common sign would be the negative. And they were y terms before I combined them, so they're still y terms after. And then that's going to be it. We can't go any further because these two aren't like terms. This has an x for its variable, and this one has a y, and to be like terms they have to have the same variable factors. And then just a quick note, if I had tried to combine the 7y and the -2y before I cleared the parentheses, I would have gotten +7 minus 2 would have been 5y, and that is different than what I had down here. So when you're going to combine like terms, make sure you do clear parentheses before you try and do your combining. So let's keep that in mind as we go on to the next couple. So let's see. This one, we don't have to kind of imagine a number out front. We have a number out front, so we're going to distribute that. -2 times x would be -2x, and then -2 times -3 would be +6. And then I'm going to continue on at the same time. Go ahead and clear parentheses on that second part. -7 times x would be -7x, and -7 times +2 would be -14. So we've cleared our parentheses, so that clears the way for us to go ahead and start combining like terms. We have two x terms right here which are like terms. Again, make sure you attach the negative as part of the term. So we have -2 plus -7, which is -9, and those would still be x's. And then constant terms are like terms with each other, so we have a +6 and a -14, and 6 minus 14 would be -8. So that's our answer to that one. And then one more, just a little adjustment on that. What if we have fractions when we're clearing parentheses? And the quick thing I would say there is that doesn't change the rules at all, but it does make it a little harder or take a little longer to carry that out. the rule would still be, let's go ahead and distribute that number out front to clear our parentheses before we combine like terms. And if that's a fraction, it just means we're multiplying by a fraction. And really, to me, the big difference that makes is I might not be comfortable doing the multiplication in my head at this point, so I would write it out. I have negative 1/3 times 6x, and then I have negative 1/3 times 9. And notice I am distributing not 1/3, but negative 1/3. Most common mistake that I see on problems like this is to forget to do the negative on the second term. And then before I start trying to combine anything, I want to carry out the multiplications. And fortunately for us here, our denominator has common factors with each of the terms that were inside. So this 3 goes into that 6 twice. This 3 goes into that 9 3 times. And because our denominators have been canceled, we can say that we're not going to have fractions anymore. So let's see what we do have. We have that 7x, which we haven't really messed with. And we have negative 1 times 2 times x. That would be negative 2x. And then we have negative 1 times 3, which would be negative 3. And most of our work is done here now. We've gotten rid of our parentheses, we've gotten rid of our fractions, but we do still have these like terms right here. So 7x minus 2x would be 5x, and then we still have that minus 3. And that would be our answer on that one. So the rule wasn't different there. We're still distributing to clear parentheses and then combining like terms by adding their coefficients. Just took us a little bit longer to carry that out when we had fractions involved. And I was inclined to show a little bit more work because of that too. Alright, so we just have one final example here. And they want us to draw a graph of this equation. And if we were to look at this equation, we might not initially know what kind of graph that was, but perhaps if we simplified it, we would get to a form that we recognize, and that's what they want us to do. So let's go ahead and start out by distributing that negative 2, just like we were doing on our other problems. The y is all by itself and simplified, so I'm just going to copy that down. But I am going to go ahead and start distributing and simplifying over here. So negative 2 times 3 would be negative 6x, and a negative 2 times a negative 2 would be a plus 4. And then this 5x would not get distributed with a negative 2 because it's a separate term. It was not inside those parentheses, so that's just going to be copied over. And just like in the examples above, once we have cleared parentheses, we'd want to combine our like terms, and just remembering this is not a 6x, but a negative 6x. So y equals, and we have negative 6x plus 5x. Negative 6 plus 5 would be negative 1, or I could just write negative x, and then we have the plus 4. So that's been simplified now, which is part of what they asked us to do, simplify the right-hand side. So I could box that, if you want, as my answer. But they also want me to graph it. Well, we might not have known what the graph was here, but now this looks like our standard form y equals mx plus b. So this is going to be the graph of a line, and it's easier to see that now that we've simplified. So I usually think the easiest way to do a graph, especially when it's in the y equals mx plus b form, is to just go ahead and make a quick table. So if we put 0 in, we'll be finding the y-intercept, and we could plug it in, but we know this constant term is always going to be the output when we plug in 0 in this format. And then I just want to pick another x term to plug in. So let's see, what if I plug 3 into that equation? So substitute that in for the x, and then add the 4. I have negative 3 plus 4, that would be 1. So there's another ordered pair. And I'm going to go ahead and just use those to do my graph. None of the numbers are real big, so I could use the standard scale of 1s. And usually a good idea to go ahead and label our axes, even if in this case it's the standard variable, so that would be what people would probably guess, but let's go ahead and just make that clear by labeling them. And then plot our 2 points, so over 0, up 4, and then over 3, 1, 2, 3, up 1. And those 2 points should be enough for us to get our line. So I'll throw the ruler on there. Get that lined up, and then just draw the line in, and that would be our graph. And I would say we're done with the work by hand, but they did ask us to verify that on the graphing calculator. So there's kind of a couple things that we'd be doing here. We could just draw our graph and make sure that it kind of matches our picture right here, but we could also do what we did on the previous ones and graph both the left hand side and the right hand side and make sure that they vary, or that they match up with each other. So I'll go ahead and do that. So let's see, starting off, I would go to the y equals menu. I'd get rid of those examples from before. I would put in our original expression, -2 times parentheses 3x minus 2 plus 5x. That was our starting point, and I believe we ended up with -x plus 4. So I'll put that in as well. And I'll hit graph, and this time I'm hoping for a couple things to happen. Like before, I'm hoping that this graph and that graph overlap each other. But I have an additional piece this time as well. I did this graph by hand, so I'm also hoping it looks like this picture. So it does look like the picture. That's a good sign. Now let's see if they overlap each other. I'm not seeing a second graph, so that's a good sign as far as that goes. Let me use the trace to kind of make sure that they're really one on top of another. Here's our y1 graph, and we can see that we're on the line. Now I've switched to y2, and my little flasher is still in the exact same spot, so that's a good sign. Alright, that's it for section 4.2.